had found the time period of the oscillations, be it linear oscillations or be it angular oscillations, using the concepts of force and torque. When it was linear SHM, over there we displace the body by a small distance y, we find a restoring force, and then we find the acceleration. We prove acceleration proportional to minus y, hence this is SHM, and we use the formula T is equal to 2 pi under root y by a. When we were talking about the angular SHM, over there, instead of displacing the body by a small distance y, we displace the body by a small angular displacement theta. In linear SHM, we talk about the force. Over here, in angular SHM, we talk about the restoring torque. We said in linear SHM, F is equal to ma, that is restoring force is equal to mass into acceleration. In angular SHM, we say restoring torque is equal to I into alpha. When we apply this, torque is equal to I alpha, we know that is we have to be cautious, that is torque, I and alpha, they are about the same axis. Then in linear SHM, we say acceleration is proportional to minus y, and in angular SHM, we intend to prove that is angular acceleration is proportional to minus theta. Over there we say T is equal to 2 pi under root y by a. Over here in angular SHM, we say T is equal to 2 pi under root theta by alpha. So this is how we found the time period or frequency. Frequency, you know, that is linear frequency is 1 by T. If someone talks about angular frequency, that is omega. So this is how we found the time period or linear frequency, be it linear SHM or be it angular SHM. But is there any way, apart from, let's say, using the forces and torques, any other method that is by which we can find the time period or linear frequency? Yes, it is. We can also use energy conservation method to find the time period or frequency of the oscillations, be it angular oscillation or be it linear oscillations. Over there, the method is slightly different. Over here, what we do is, that is, when we had been dealing with the forces and torques, over there we displace the body by a small distance y, and then we find the restoring force. When we use the energy conservation method, over there we are not bothered, let's say, displace the body by a small distance y from its mean position. No, we are not bothered about it. We simply say we find at any arbitrary distance, when the body is from its mean position, at any arbitrary instant, we find its mechanical energy, total mechanical energy. And this arbitrary instant is not the mean position nor the extreme positions. Because in the mean position we have primarily kinetic energy and no potential energy of the system. Whereas at the extreme position we have primarily only potential energy and no kinetic energy. So what we choose the instant, that is this arbitrary instant what we are talking about, it is about the mean position and about the extreme position, so that this body is somewhere over here and it has both the things. It has potential energy also and it has kinetic energy also. Then we say potential energy plus kinetic energy, that is constant, because these oscillations, they are not damped oscillations. When the oscillations, they are not damped, there are no friction, etc. So it means that these oscillations, they will continue for the time infinity. So once we apply conservation of energy, we find the total mechanical energy of this system at that instant. Then what we say, because this is constant, we differentiate it with respect to time. It's a very, very simple differentiation. It is very basic concepts of calculus, because in our conservation of mechanical energy, we have potential energy also, we have kinetic energy also. And when we have kinetic energy, it means there is velocity also, half mv square velocity also. And when you differentiate it, then from the velocity component, when we differentiate with this time, we get some acceleration expression also. Once again, we prove that is acceleration proportional to minus y, or alpha is proportional to minus theta, if this is angular or if this is linear, depending on what is the case like. And once again from there, we apply the same thing, that is T is equal to 2 pi y under root y by a for the linear SHM, and for the angular SHM, we say T is equal to 2 pi under root theta by alpha. Let's understand step by step, that is what are the steps, like what we discussed in linear SHM. We had written some steps. What is the first step? First step is displace the body by a small distance y, and the second step is find the restoring force, and so on. In angular SHM also, we had discussed some steps to find the time period or frequency. How to find the time period or frequency of SHM, be it linear SHM or angular SHM, using energy conservation method. Here also we have some steps. If we follow these steps, we can easily find the time period or frequency of the oscillations. Let's see what are these steps. So over here, when we apply the energy conservation method to find the time period of SHM, we have to very clear that is now this is different method. So we shall not be using the same step what we had been using when we had been using a concept of force and torque. That is, over there we had been displacing the body from its mean position by a small distance y or by a small angle theta. So over here, when we are doing energy conservation method, we shall no longer be using those steps. Though when we come to point number 2, It says we intend to prove that is accretion is proportional to minus y. This is for linear SHM. And if we are talking about the angular SHM, over there we shall try to prove that is alpha is proportional to minus theta. Once this is proved, then for linear SHM we can use this formula, that is t is equal to 2 pi under root y by a. And if this is angular SHM, you know it very well, that is we use t is equal to 2 pi under root theta by alpha. Over here in energy conservation method, the first thing is we'll look for what is the total mechanical energy of this system where the oscillations they are not damped. That is, we talk about the mechanical energy, we talk about the potential energy, and we talk about the kinetic energy. Over here, one important thing is we don't start when we apply the conservation of mechanical energy principle. We take any arbitrary instant. We take this any arbitrary instant when oscillating body is at a distance y from the mean position, or that is also called the equilibrium position. It is at a distance y from the mean position. Over here, avoid taking the mean position or the extreme position. Because of mean position, we have only the reflection of kinetic energy only, and whereas the extreme position, we have only expression for the potential energy. But if we take any arbitrary instant which lies between the mean position and extreme position, so we have both the things. We have potential energy also, we have an expression for the kinetic energy also. So we write the expression for total mechanical energy, that is in terms of potential energy and kinetic energy, and we put it equal to constant, because these oscillations, they are not damped oscillations, there is no friction, etc. All the forces, they are conservative forces. So that's why total mechanical energy of this system is constant. Then next step, what we do is we differentiate this energy equation with respect to time. So we know that there is something, that is velocity is there when differentiate, then certainly dv by dt it will appear, and that will be equal to acceleration. So from there we will get some acceleration expression. Once we get acceleration is proportional to minus y, we can easily say that this is SHM. While proving that is acceleration is proportional to minus the displacement in the case of linear SHM, we may have to refer to the equilibrium position or mean position, and over there we have to see that is what are the forces like which are balancing each other, and from there we may get some substitution which can be used in this equation, which has been now energy equation, which has now been differentiated with respect to time. After that we should be able to prove that is acceleration is proportional to minus of displacement, and once it is proved, then t is equal to 2 pi under y by a for the linear SHM, and once this is found, then in case linear frequency is asked, we can simply put as 1 by t, and we can get the frequency of the linear SHM. Let's understand this by taking some examples.